Welcome, curious minds. Today, we're taking a deep dive into something absolutely foundational to, well, pretty much every digital interaction you have.
Yeah, it's about how computer systems protect themselves and, by extension, your data.
Exactly. And this isn't just about keeping the bad actors out, though that's definitely a huge part of it. It's also about making sure everything inside your device runs smoothly, reliably, and basically as intended.
Right, it's internal order.
So we're going to unpack Chapter 17 on protection from that cornerstone text, Operating System Concepts, by Silberschatz, Galvin, and Gagne.
A classic.
Our mission here is to kind of shortcut you to being genuinely well-informed on this topic. We'll cover everything from the core principles right up to advanced stuff like sandboxing.
And we'll keep it in plain English with plenty of real-world examples.
Absolutely.
That's right. People often throw around the term security as this big, all-encompassing umbrella for keeping systems safe.
Sure.
But protection is actually a more specific, and I'd argue equally critical, layer under that umbrella.
Okay, so how do they differ exactly?
Well, think of security as guarding all your resources against things like unauthorized access, malicious destruction, or even just accidental inconsistency.
Right, the external threats and big accidents.
Exactly. What's really fascinating about protection, though, is it zeroes in on controlling the access of individual processes and users to those resources within the system itself.
Ah, so it's the internal traffic cop.
Precisely. It's the gatekeeper, constantly deciding who gets to do what, where they can do it, and when.
So if security is the what are we defending against, protection is more the how do we manage access internally. Why is that internal gatekeeping so important then? What's the real need for this layer?
Well, the most immediate reason, obviously, is to prevent deliberate misuse by users or programs.
Yeah, stopping bad intentions.
But it's actually much broader than that. It's fundamentally about ensuring every single process, every piece of software running, uses the system's resources exactly how it's supposed to. And this isn't just like a nice-to-have feature. It's an absolute requirement if you want a reliable system. Protection also massively improves reliability by catching errors right at the interfaces between the different software components.
Ah, so it stops one bad apple spoiling the bunch.
Exactly. Without it, one glitchy program could potentially corrupt data used by another, or even bring down the entire system. It's like having firewalls inside your house, not just guarding the front door.
That makes perfect sense. So setting clear boundaries and enforcing them rigorously. Now, I hear there's a key distinction often made in this area, mechanism versus policy. Can you break that down for us? What does that actually mean?
Right. This is a really important distinction. It basically raises the question, who gets to decide what's allowed and what isn't?
Okay.
Policies dictate what will be done. For example, a policy might state which specific users are permitted to access a certain file, or what kind of data can move from one part of the system to another.
So the rules.
The rules, exactly. Mechanisms, on the other hand, determine how it's done. They're the underlying tools, the structures, the actual code the operating system provides to enforce those policies.
Yeah, enforcers.
Right. And this separation is crucial for flexibility. Policies, they can change quite often. Maybe your company updates its data access rules, or you install new software with different needs.
Sure.
But the underlying mechanisms, the enforcers, should ideally remain general and robust enough to adapt to those new policies without needing a complete system overhaul every time.
So policies are the changeable rules. Mechanisms are the stable enforcement tools.
Got it. Are there any guiding principles, like core philosophies, that designers follow when they're building these intricate protection systems?
Oh, absolutely. The most important, truly the cornerstone principle is the principle of least privilege.
Least privilege sounds minimal. It is, and that's the point. It's deceptively simple, but incredibly powerful. It dictates that programs, users, even parts of the system itself should be given just enough privileges to perform their specific designated tasks and absolutely no more.
Just enough, so it limits the potential damage if something goes wrong.
Precisely. Think about it like an immune system that only activates exactly where it's needed with just the right amount of force. Can I get you a quick example?
Please do.
Okay, think about UNIX or Linux systems. Most of the time, you shouldn't be running as root, the super user, unless it's absolutely critically necessary.
Right, I've heard that. Why not?
Because root is virtually omnipotent. It has access to everything. If you're logged in as root and you make a simple typo in a command, or worse, if a malicious attack compromises a root session,
Uh-oh.
the damage could be catastrophic, system-wide. By limiting privileges routinely, you mitigate that blast radius. If your word processor only has permission to access its own document files and maybe print, then even if it gets compromised by some malware, it can't suddenly start deleting your core system files or reading your emails. Its potential for harm is strictly limited.
That's a really clear example of containment.
Hmm.
What other big ideas underpin protection? Are there related principles?
Yeah, closely related is compartmentalization. This is all about protecting individual system components with very specific, tailored permissions.
Breaking things down.
Exactly. If one part gets compromised, the damage is contained within that compartment, preventing it from spreading easily to other parts of the system. Think of it like a ship with watertight compartments.
If one section floods, the whole ship doesn't necessarily sink.
Precisely. And then there's defense in depth. This is the idea of applying multiple overlapping layers of protection. No single defense is ever perfect, right?
Right,
So you
yeah.
stack them. It's like a medieval castle. You don't just rely on the outer wall. You've got the garrison, the outer wall, maybe an inner wall, a moat.
Layers upon layers.
Yes. Because attackers often use multiple methods too, leading to this sort of perpetual security arms race. And alongside these defenses, systems often generate an audit trail.
Logging everything.
Meticulously tracking access events, yeah. This isn't just for figuring out what went wrong after an attack. It can reveal deviations from normal behavior, giving you early warnings before disaster strikes.
Okay, so we've explored the why, the goals, the principles, like least privilege and defense in depth. Now let's get into the nuts and bolts. How are these principles actually enforced? How do we build the walls? I've heard about protection rings. What's the deal with those?
Protection rings. They're a really popular and quite elegant model for separating privileges, and importantly, they require direct hardware support from the CPU.
Hardware level, okay.
Imagine a set of concentric circles, like the layers of an onion, or maybe target rings.
Got it.
Ring 0 is the innermost core. This is typically where the kernel, the absolute heart of the operating system, runs. It's the most privileged layer with complete power over the entire system.
The bullseye.
Exactly. As you move outwards to ring 1, ring 2, ring 3, and sometimes more, though often it's just 0 and 3, the privileges decrease significantly. User applications, like your web browser or word processor, usually live way out in ring 3.
The outer edge with the least power.
Right. They have significantly limited capabilities compared to the kernel in ring 0. Intel architectures, for example, commonly use this ring 0 for kernel, ring 3 for user code setup.
And what about ARM? They're huge in mobile.
ARM has evolved its approach. Initially, they had simpler modes like user USR and supervisor SVC, but modern ARM processors, especially in phones and embedded systems, have features like Trust Zone.
Trust zone. Sounds secure.
It really is. Think of it as creating a highly secure, almost separate execution environment within the main processor, backed by hardware security features. It's like a hardware-protected safe inside the chip.
Wow.
Even the main operating system kernel running in its privilege mode can't just barge into Trust Zone. It has to formally request services using a special instruction, the Secure Monitor Call, or SMC.
It's another layer of separation.
A very strong one, yeah. This is used for really sensitive stuff like managing the on-chip cryptographic keys used for, say, your phone's fingerprint scanner or secure payments. Android uses Trust Zone extensively. And ARMv8 extended this even further with exception levels, EL0 to EL3, where EL3 is often Trust Zone, the most privileged. Some systems use this for things like checking the kernel's integrity hasn't been tampered with. It's defense in depth built right into the silicon.
That's fascinating. So the chip's architecture itself creates these fundamental layers of privilege. That's much deeper control than just software.
Yeah.
Okay, so with that hardware foundation laid, how do we then manage permissions for all the software objects we interact with? Files, programs, devices.
Right. That brings us nicely to the concept of the domain of protection. At its core, you can view a computer system as this vast collection of processes running programs and objects.
Objects being?
Objects can be hardware things like the CPU itself, segments of memory, a printer, a network card, or they can be software things, files, directories, databases, programs, even internal OS structures like semaphores used for synchronization.
Okay, so basically anything that can be accessed or manipulated.
Pretty much. And each of these objects has a defined set of operations that can potentially be performed on it, like read, write, execute, delete for a file, or connect, send, receive for a network socket.
Gotcha.
The underlying philosophy here, closely related to least privilege, is the need-to-know principle.
Need to know. Sounds like spy stuff.
Yeah, maybe a little. But the idea is simple. A process should only be able to access those specific objects it currently requires to perform its immediate task and nothing else.
So no unnecessary access.
None. For instance, think about a compiler program. Its job is to take your source code file and produce an executable file.
Right.
So it needs read access to the source file and write access to the output file. It absolutely should not need or get access to read your email or write to random system configuration files.
That makes sense. Limits the damage if the compiler has a bug or gets hijacked.
Exactly. When enforced properly, this principle significantly limits the potential fallout if a process goes rogue or contains a vulnerability. You can kind of think of need to know as the policy you're trying to achieve, access only what's needed now, and least privilege is a key mechanism or principle to help you enforce that policy.
Okay, so we have all these processes, all these objects, and these very specific permissions linking them based on need to know. How on earth do operating systems conceptualize and manage all these relationships? It sounds like it could get incredibly complex very quickly.
It definitely can. To visualize and reason about this complexity, computer scientists often use an abstract model called the access matrix.
Access matrix. Okay, picture time.
Imagine a giant grid, like a spreadsheet. The rows represent domains. A domain is essentially a collection of access rights, often associated with a user or a specific process running on behalf of a user.
So each row is like a who or a what context.
Exactly. And the columns represent all the objects in the system, every file, every printer, every memory segment, you name it.
Got it. Rows are domains, columns are objects.
Right. Now, each cell in that grid, where a row domain intersects with a column object, specifies exactly what operations a process executing within that domain is allowed to perform on that specific object.
So cell D1, F1 might say read-write.
Precisely. Domain D1 can read and write file F1, but maybe cell D1, F2 only says execute, meaning D1 can run program F2 but can't modify it.
That seems like a clear way to lay it all out.
It is. And what's really powerful about the model is that this matrix doesn't have to be static. We can actually model dynamic changes within the matrix structure itself.
How so?
Well, for instance, we can treat domains themselves as objects. So an entry in the matrix, say access ij, where I is domain die and j is domain dj viewed as an object, might include a special switch, right?
A switch.
Yeah, this would allow a process running in domain die to temporarily switch into domain dj, maybe to perform some privileged operation that only dj is allowed to do, and then switch back.
Ah, like temporarily putting on a different hat.
Kind of, yeah. Or you might have copyrights. An asterisk next to a right in a cell, like read, could mean that a process in that domain can not only read the object, but can also copy that read permission into another cell in the same column, effectively granting read access to another domain for that object.
Passing on permissions.
Exactly. There are also concepts like an owner right, which might let a domain add or remove any valid right within that object's column, or a control right for a domain object, letting one domain modify the permissions of another domain.
That's a very elegant model for controlling who can do what. But I recall you mentioning something earlier about a confinement problem. You said the access matrix doesn't solve it. What's that about?
Ah, yes, the confinement problem. This is a really tough nut to crack. While the access matrix is fantastic for controlling explicit access rights, who can read, who can write, who can switch it, doesn't generally solve this deeper, more subtle challenge. Imagine you have highly sensitive information inside a protected domain. Confinement is about trying to guarantee that no information whatsoever about that sensitive data can leak outside that domain's environment.
Not just preventing direct reads, but any leakage.
Any leakage at all, even indirect leakage, maybe through timing channels or manipulating shared resources in a way that reveals something. For example, if you process top secret data, how do you ensure not one bit of information about it can ever escape, even if direct file access is blocked?
That sounds hard.
It's incredibly difficult. Achieving absolute containment, guaranteeing zero information leakage under all possible circumstances is generally considered unsolvable in the general case. It highlights a fundamental, persistent limitation, even in our most sophisticated protection systems.
Wow, that's a really thought-provoking challenge. Okay, so the access matrix is this powerful, if not perfect, theoretical model. How do operating systems actually implement something like that in the real world? You said yourself, a full matrix for a complex system would be astronomically huge in mostly empty space.
You're absolutely right. It would be incredibly sparse and wildly inefficient to store directly as a giant grid. So operating systems use different, more practical approaches that capture the spirit of the access matrix.
Like what?
Well, the simplest conceptual implementation is a global table. Just one massive list of tuples where each tuple is like domain, object, right set.
So they're just listing every single permission explicitly.
Yeah. But as you can imagine, this table would be enormous, probably too large to keep entirely in memory, making lookups potentially slow.
Impractical. Okay, what else?
A much more common approach is using access control lists, ACLs, often just called access lists, associated with objects.
So the list lives with the file, or the printer.
Exactly. Each object, like a file, has its own list attached. This list specifies which users or domains can do what to that specific object. When you try to access the file, the system just checks the file's personal ACL.
Ah, like standard file permissions in Windows or Linux.
Precisely. That's a classic example of an ACL implementation. It's focused on the object. Who can touch me?
Okay. Is there an opposite approach?
There is. It's called capability lists associated with domains. In this model, each domain, or maybe each process, holds its own list of what it is allowed to do.
So the list lives with the process.
Right. Instead of the file listing who can access it, your running program carries a capability for each object it can access. Think of a capability as a secure, unforgeable token or ticket.
Like a key.
Exactly like a key, or maybe a secure pointer that not only identifies the object, but also encodes the specific rights the process has for that object. For example, read access to file X. Access is granted simply by possessing a valid capability. The OS's main job then becomes protecting these capabilities themselves, making sure they can't be stolen or forged.
Okay. ACLs focus on the object. Capabilities focus on the domain process. They sound like two sides of the same coin. What are the trade-offs? Why choose one over the other?
That's the crucial question. There's a significant trade-off. Access lists, ACLs, are generally simpler for users and administrators to understand and manage. You look at a file, you see its permissions. Easy.
Makes sense.
But finding out all the things a specific user can do across the entire system can be quite inefficient. You'd have to potentially check the ACL of every single object.
Right, scattered information.
Exactly. Capability lists, on the other hand, are highly efficient for verifying access. The process already holds its ticket, its capability. The check is quick.
But it's always a but.
The but is revocation. Taking away access rights in a capability-based system is much, much harder.
Why is that?
Because capabilities are distributed. They're like physical keys handed out. If you give out 1,000 keys to a vault and then decide one person shouldn't have access anymore, how do you get just their key back?
You'd have to track it down or change the lock.
Exactly. You either need complex schemes to find and invalidate that specific capability, like backpointers or indirection, periodically expire all capabilities and reissue them, or use cryptographic keys that can be centrally revoked. It's complicated. With access lists, revocation is simple. You just go to the objects list and delete the entry for the user you want to block. Done.
Ah, I see. Centralized control versus distributed efficiency, with revocation being the sticking point for capabilities. That's a really clear breakdown. So we've covered the theory, the models, the implementation choices. Now let's get practical. How do real-world operating systems, the ones we use every day, actually put these concepts into practice? Can you give us some concrete examples?
Absolutely. Let's start with a classic mechanism from the UNIX world. The set-to-id bit.
Set UID. Okay.
It's a special permission bit you can set on an executable file. If that bit is enabled when any user runs that program, the program temporarily executes with the privileges of the file's owner, not the user who launched it.
Hang on. So if a file is owned by root, the super user,
And it has the set-to-id bit set.
then when I run it, even as a normal user, it runs as root.
Temporarily, yes, for the duration of its execution. This is actually how essential tasks work, like changing your own password. The UN Urban Password Program needs to modify the system's password file, which is usually owned by root and protected.
Right, I can't edit that file directly.
No, but the password program itself is owned by root and has the set-to-id bit set. So when you run it, it temporarily gains root privileges just long enough to update your password in the protected file, and then it exits, dropping those privileges.
Okay, pause right there. You just described a mechanism where a normal user can trigger a program to run as the all-powerful root. My mind immediately screams, security nightmare. Is it really as precarious as it sounds?
Your instinct is spot on. It is an inherently high-risk mechanism. For set-to-id binaries to be safe, they have to be absolutely perfectly programmed. They need to be what we call sterile and hermetic.
Meaning?
Meaning they must be completely tamper-proof, handle all inputs with extreme suspicion, and operate in a highly controlled way, doing only the one specific privileged task they need to do and nothing else, then exiting cleanly.
And is that easy to achieve?
History shows it's incredibly difficult to get right every single time. Experience has unfortunately demonstrated again and again that vulnerabilities in Situate programs have been frequently exploited by attackers to gain root access, what's called privilege escalation. It's a powerful tool, yes, but one that requires immense caution and has often been a weak point.
Okay, noted. Powerful but dangerous. What about more modern systems, like mobile OSs?
Shifting to, say, Android, it offers a great example of using basic protection concepts for quick, simple, but effective isolation between apps.
How does it do that?
Android assigns a distinct Linux user ID, UID, and group ID, GID, to each application when it's installed. All the files and data created by that app belong to that specific UID.
So each app is like its own user.
Effectively, yes. The standard Linux file permissions then automatically prevent App A from reading or writing App B's private data because they have different UIDs. It's a straightforward way to sandbox apps from each other. Android can even use special isolated UIDs for certain processes to further restrict their ability to communicate with other parts of the system, adding another layer for privacy.
Clever use of existing mechanisms. So systems have clearly evolved beyond just simple UIDs and the occasional risky Situate. What are some of the more cutting-edge ways protection is handled in modern operating systems? Are things getting more granular?
Oh, definitely. Modern OSs offer far more sophisticated and granular control. One really significant approach is role-based access control, RBAC. You find this in systems like Solaris 10 plus MAE, and it's common in enterprise environments.
RBAC, how does that work?
Instead of assigning permissions directly to hundreds or thousands of individual users, which gets messy fast, you define roles. Think system administrator, database manager, web editor, backup operator, guest.
Logical groupings.
Exactly. Then you assign specific privileges to each role. A privilege might be the right to execute a certain sensitive system call or access a particular configuration tool. Finally, you just assign users to one or more roles.
So the user inherits the role's privileges.
Precisely. This beautifully implements the principle of least privilege because users only get the exact set of rights needed for their job function defined by their role. It makes managing permissions much simpler, consistent, and less error-prone than dealing with individual user permissions.
That sounds much more manageable. What else?
Another major advancement, moving beyond traditional models, is mandatory access control. MAC.
Mandatory. That sounds stricter than what we usually see.
It is. It's fundamentally different from the discretionary access control, DAC, that underlies typical UNIX file permissions or Windows ACLs.
How so? Discretionary means?
Discretionary means the owner of an object, like the user who created a file, has the discretion to decide who else gets access and what kind of access they get.
Right. I can set permissions on my own files.
With MC, that discretion is removed. Access is enforced by a strict, system-wide policy defined by the administrator. And critically, even the root user or system administrator cannot obey this policy.
Not even root. Wow. How is it enforced then?
MC systems typically use labels or security levels. Think classifications like unclassified, confidential, secret, top secret. These labels are assigned to both objects, files, network ports, devices, and subjects. Processes, users.
Labels on everything.
Yes. Access is then granted or denied based on a fixed set of rules comparing the subject's label, their clearance, to the object's label, its classification. For example, a policy might state that a process running with a secret clearance can read unclassified and secret files, but is absolutely forbidden from writing data down to an unclassified file to prevent leaks, and perhaps cannot even see that top secret files exist.
That sounds incredibly robust. Where do we see MB used?
It's used in high security environments, of course, but variants are now quite common. So Linux, security enhanced Linux, trusted BSD, which influenced parts of Macro security, and Windows Mandatory Integrity Control, MIC, introduced in Vista, are all examples of MMAC implementations making their way into mainstream operating systems. It's all about preventing privilege misuse, even by legitimate administrators, whether accidental or malicious.
That sounds like a really powerful multi-pronged attack on vulnerabilities, pushing protection way beyond simple ownership. What other innovative techniques are out there these days, helping to secure our digital lives?
Yeah, the evolution continues. We're seeing refinements of older ideas and entirely new approaches. For instance, Linux capabilities and Darwin entitlements used by Apple are contemporary takes on capability-based systems.
Thought they were.
Instead of the all-or-nothing power of root, Linux capabilities essentially slice up root's traditional superpowers into dozens of distinct fine-grained privileges, like the capability to change network settings, the capability to load kernel modules, the capability to bypass file permissions.
So you can grant just the specific bits of power needed.
Exactly. A process might only need one or two specific capabilities rather than full root access. Darwin entitlements, used in macOS and iOS, are similar in spirit but work differently. They are often declarative XML snippets embedded right into an application's code signature.
Built into the app itself.
Yes, stating what sensitive resources or operations the app needs access to, like accessing your location or contacts. The OS verifies this signature and the requested entitlements before granting access.
Very cool. What else is new?
Then there's System Integrity Protection, SIP, which Apple introduced in macOS 10.11 El Capitan. This was a big step.
SAP. What does it protect?
It actively restricts everyone, including the root user, from modifying critical system files, directories, and even kernel extensions. It puts core parts of the OS off limits to tampering, even by the administrator. It also enforces strict code signing requirements for things like kernel extensions, ensuring only Apple-approved or properly signed code can run at that deep system level.
Locking down the core OS.
Yeah.
Makes sense.
We also see more sophisticated system call filtering. This is a really effective technique.
Filtering system calls. How?
It involves adding code, often leveraging frameworks like Linux's secomp BPF, secure computing with Berkeley packet filter extensions, right into the kernel. This code acts like a bouncer, inspecting every single system call a process tries to make.
Checking every request to the OS.
Exactly. It allows the system to restrict a process to only a small, predefined, safe subset of system calls. Or even more powerfully, it can inspect the arguments being passed to those calls to block known exploits. For example, it could block a call trying to exploit a known vulnerability in Linux's futex system call used for mutexes.
So it can stop attacks, even if the vulnerability technically exists.
Potentially, yes. The challenge is defining the right filter rules strict enough to be secure, but flexible enough not to break legitimate applications, ideally without needing constant kernel recompilations.
Tricky balance.
Very. Building on that idea of restriction, we have sandboxing. This is huge now.
Sandboxing. Putting apps in a little box they can't escape.
That's the essence of it. It runs processes in incredibly tightly limited, isolated environments. The key is that these strict, often nearly insurmountable restrictions are imposed very early in the process's startup, and the process itself usually can't remove them.
So even if it gets compromised.
The damage is contained within that sandbox. Because the sandbox process literally lacks the permissions or mechanisms to communicate with other system components, access most files, or reach the network, unless explicitly allowed by its predefined sandbox profile.
Where do we see this?
Everywhere. Web browsers heavily sandbox tabs and rendering processes. Java and .NET platforms have used VM-level sandboxing for ages. Android uses a combination of Linux policies and secomp BPF for its app sandboxes. And Apple has its Seatbelt framework, which provides highly customized sandbox profiles and is now mandatory for apps submitted to the App Store.
Seems essential for modern security. Anything else?
And of course, we can't forget the ever-crucial code signing.
Digital signatures on software.
Right. Using cryptographic hashes and digital signatures, developers can sign their programs and executables. It acts like a tamper-evident seal and an authenticity guarantee from the author.
How does the OS use it?
Many modern operating systems, iOS, Windows, macOS are prime examples, will check this signature before running a program. If the signature is missing, invalid, meaning the code was altered after signing, or belongs to an untrusted developer, the OS may simply refuse to run the program or at least warn the user very strongly. It's a fundamental check against malware distribution and ensures software integrity.
That's an impressive array of tools and strategies, layers upon layers of defense, constantly evolving. But all of that seems focused on the OS, or hardware enforcing rules on programs. What a protection built directly into the very fabric of programming languages themselves. That sounds like a whole different paradigm.
It absolutely is, and it's a really fascinating and powerful area called language-based protection.
Language-based. So the language enforces the rules.
Exactly. Instead of relying solely or even primarily on the operating system kernel to be the ultimate gatekeeper, the programming language itself can specify and enforce protection policies.
How would that work?
There are a couple of main approaches. In a compiler-based approach, protection requirements are declared right within the language syntax, maybe as extensions to data types or special annotations.
So the programmer declares the intent.
Right. This can simplify things immensely for the developer. The compiler then analyzes the code and automatically generates the necessary checks and safeguards directly into the compiled program. The neat thing is this makes the protection policy potentially independent of any specific operating system.
Interesting. What's the other approach?
The other is runtime-based enforcement, and Java is the classic example here.
Java. Security was always a big part of its design.
It had to be, because a core idea of Java was the ability to dynamically download and run untrusted code, like applets, safely from across a network. The Java Virtual Machine, JVM, which runs the Java bytecode, has extensive built-in protection mechanisms.
Like what?
Well, each piece of code, each class, loaded by the JVM, gets assigned to a specific protection domain based on where it came from, local file, specific website, and its digital signature. This domain dictates its permissions.
Okay.
But the really clever part is how it handles calls between code from different domains, especially when privileged operations are involved. It uses a mechanism often called stack inspection.
Stack inspection. Sounds like looking backwards.
That's exactly what it does. Imagine a security checkpoint that doesn't just check the ID of the person right at the gate, but asks to see the IDs of everyone in the chain of command who told that person to come to the gate.
Checking the whole chain of calls.
Precisely. When a piece of code tries to access a protected resource, like opening a file or network connection, the JVM doesn't just check the immediate caller's permissions, it walks back up the entire call stack of the current thread.
Why do that?
To prevent sneaky privilege escalation. Maybe an untrusted applet calls a trusted library function, which then tries to perform the sensitive operation. Stack inspection ensures that somewhere in that call chain, typically close to the trusted code, there's an explicit assertion of privilege, using a special do privilege block in Java. If the entire chain doesn't have the necessary permissions, or if the untrusted code is the ultimate originator without specific privilege being asserted later, the access is denied.
So it stops untrusted code tricking trusted code into doing bad things.
Exactly. It prevents indirect, unauthorized access. And underpinning all of this in Java is type safety.
Type safety. Making sure variables have the right kind of data.
Yes, but it's more profound than that in this context. Because Java is type-safe, programs are prevented from doing things like forging pointers, directly manipulating arbitrary memory locations, or casting objects to incompatible types. This means objects can only be accessed through their well-defined methods, the public interface, rigorously enforcing encapsulation and preventing many common security vulnerabilities found in languages like C or C++A, or the language structure itself becomes a core part of the protection mechanism.
So wow, protection really is everywhere, from the CPU hardware itself, through the OS kernel, system utilities, sandboxing frameworks, right into the programming languages we use. What does this all mean for us, the users, and maybe for the future of computing?
Well, this deep dive really hammers home that protection isn't some static feature you just switch on. It's this constantly evolving, dynamic process, almost an arms race, like we said earlier. You have layers upon layers of diverse mechanisms and policies working together, from those hardware rings deep inside the processor, through the OS's access controls and MS policies, up to sophisticated software sandboxes and even language-level enforcement in things like Java.
It's complex.
It is. And the core idea, the thread running through it all, remains that constant vigilance, adaptation, and the strategic application of those foundational principles, least privilege, defense in depth, compartmentalization, are absolutely essential for maintaining system integrity. Especially in our increasingly complex, interconnected digital world, it's fundamentally about how we build and maintain trust in environments that are almost by definition untrusted.
And looking forward, it really raises an important question for you, our listener, to think about. As our computing environments become ever more distributed, think cloud platforms, IoT devices everywhere, complex interactions between services, and increasingly reliant on shared resources, where do you think the next big innovations in protection will need to emerge? Will we see more AI-driven adaptive defenses? Maybe a fundamental shift towards radically different security architectures based on formal verification or completely new hardware paradigms? How might these future changes fundamentally alter the way we interact with our devices and safeguard our data?
That's the big question. We certainly hope this deep dive gave you a clearer, more concrete understanding of the intricate, absolutely crucial world of operating system protection. It really is the foundation for so much else.
It really is. Thank you for joining us on this deep dive.
And from the Last Minute Lecture team, thank you for learning with us.